This is Dr. P. Malliga, Associate Professor from Department of Physics, Satyabama Institute of Science and Technology, deemed to be University. And I am very glad to meet all of you in this session. Now, as you know, as part of our curriculum, we have for our first year engineering graduates a course called Engineering Physics or Physics for Engineers, in which there is a physics lab session also included. So in the physics lab session, we have nearly 8 experiments, and out of the 8 for today's session, I am going to demonstrate one experiment for you. So welcome to the class, students. So the title of the experiment that we are going to study for today is Determination of Energy Gap or Forbidden Energy of a Semiconducting Material taken in the form of a PN junction diode. So the aim of the experiment is to determine what is called the energy gap or the forbidden energy gap of a semiconductor or a semiconducting material taken in the form of a PN junction diode. Now, all of you are familiar with a PN junction diode. You know that a PN junction diode is made by placing a P-type semiconductor and an N-type semiconductor adjacent to each other. So that we call as a PN junction diode. Now, when such a junction is formed, we know there is going to be a formation of the depletion region. Now, I have drawn for you a PN junction diode which can be worked under 2 conditions. So this is your P-type semiconductor. You know, P-type means it contains majority of holes. And we know that adjacent to the P-type semiconductor, we have placed the N-type semiconductor, and as all of you know, it contains majority carriers as the electrons. Now, when such a junction is formed, there is usually what you call as the depletion region. Now, suppose if a PN junction of this type is connected to an external source or a battery, and if the P-type connected or the anode, what you call, is connected to the positive of the battery and N-type connected to the negative of the battery, we call this mode as the forward biasing mode. And you know that during this forward bias mode, there is going to be a movement of holes and electrons across a junction, and this will result in the flow of current in the junction. Automatically, the depletion region becomes narrower. That's why I've written it has a smaller depletion width. Now the status just changes if the connection of the battery is reversed. So this condition will lead to a larger depletion width wherein the flow of current in the junction or at the junction is completely negligible. It is very, very small. Rather, you can say there is no flow of current through this junction. So such a state, we call it as the reverse bias of the junction. So now this concept is very important for determining the energy gap of our semiconductor material, which we have taken in the form of a PN junction diode. Now the reverse bias condition is chosen because the current flowing through the PN junction is small and the internal heating of the junction is also small. So this aids for you to take measurement of the energy or the band energy values. Moreover, we are going to perform the experiment and we are going to determine the energy gap. We study the variation of the conductance with temperature. So these are the 2 conditions that are needed in order to determine the energy gap of the given semiconducting material. So the first condition is that to determine the energy gap, we study the variation of conductance with temperature. And your second point, reverse bias is chosen because the current flowing through the PN junction is small and internal heating of the junction is also small. Now let's understand what is the meaning of this depletion region or the meaning of energy gap. In solid state physics, energy gap or the band gap is the region between the valence and the conduction band in which the electron states are forbidden. There is no energy level for the electrons existing in this forbidden band. So that's how we can differentiate between a metal, that's a conductor, a semiconductor, and insulator based on the energy band diagram. Now, as we know, in the case of metal, the valence band and the conduction band are close to each other. Therefore, the movement of electrons from the valence to conduction band is very easy. Whereas in a semiconducting material, valence and the conduction band, they are separated by a small energy gap, which you call as the band energy or the energy gap. So that level is quite higher. You call that as the forbidden band. Now it becomes difficult for the electrons to move from the valence to the conduction band unless you give an external biasing to it, which you can do with the help of forward bias. The third step, you have what's called the insulator, where the distance or the bandwidth or the band gap is very large between the valence and the conduction band, and it is impossible to excite the electrons from the valence to the conduction band. So now our task is, since we are given a semiconducting material, we are interested to determine the energy gap or the energy that is needed for the electron to move from the valence to the conduction band. So to determine that, we have to follow a particular procedure. So we are supposed to know the circuit diagram, that is, we are going to make use of the semiconducting material in a circuit like this, and we are going to proceed with the experiment after I give you an explanation on this experimental setup. So let me first ponder over what is the circuit diagram. So now you can observe in my diagram the apparatus that I need are a 15 volt battery and a voltmeter having a range from 0 to 12 volts, a microammeter having a range from 0 to 100 microamps, and my semiconductor diode, which I am going to place it in a reverse bias mode. Now the diode is also immersed in a liquid. Rather, I can say it's going to be an oil bath. The oil can be a castor oil or a glycerin, such that it can sustain the heat that is provided in the bath. And a thermometer is provided to note down the fall in temperature or the rise in temperature as may be. Now to look at the circuit, we observe that the battery and the diode are connected with opposite polarity. So also we see that the battery and the voltmeter, they are connected parallelly. The positive of the battery connected to the positive of the voltmeter, negative of the battery connected to the negative of the voltmeter. Similarly, the positive of the voltmeter connected to the positive of the microammeter, and and the negative of the voltmeter is connected to the positive of the battery. Now let us try to follow the demonstration of the circuit diagram that I have put up on the board for you. Now if you look at this inbuilt apparatus, we have what is called the battery, the external battery that has to provide energy for your diode, and then you have a micro ammeter, okay, and then you have a voltmeter, and you are also provided with a heating mantle that is connected to this, you can see this top board, and you have a beaker that contains the liquid, the castor oil liquid inside, and the diode is immersed, well immersed inside the liquid, and it is kept inside a plastic capsule to ensure its safety. We also have a holder that holds the thermometer, and we can look at the readings range of the thermometer. Now to begin with the experimental part, we have to switch on the battery connection alone with the diode. So I am going to switch off my heater. Now at this juncture, I can observe when I rotate this terminal, there is a change in both the ammeter and the voltmeter readings. So you can see there is going to be a slight change or variation in the micro ammeter and voltmeter readings. Now once this is ensured, you know that your circuit is working. Now once you confirm that, we will switch off the battery connection and we will switch on the heater so that the liquid starts getting heated. So we are going to study, as I told you, we are going to study the energy gap. We study the variation of conductance with temperature. So we have to wait till the liquid reaches a particular temperature and the thermometer ranges to around 70 degree or a little bit above. So let me verify what is the temperature shown in my thermometer. Now after waiting for some time, we have noticed that the temperature has risen up to 80 degree. At this juncture, I am going to switch off the heating mantle and I am going to note down for every 2 degree fall in temperature, the corresponding value of my microammeter readings. Now the temperature has come to 78. I have to note down what is the corresponding value of my microammeter reading. Likewise, as the temperature falls 2 degree below, that is around say 76, I am going to correspondingly note my microammeter reading. Likewise, I am going to repeat the experiment till the temperature falls to nearly 70 degrees Celsius, that is 10 degree below 80 degree, it has attained the maximum. So for every 2 degree fall in temperature, we are going to note the corresponding value of the microammeter and tabulate in the tabular column as I am going to show in the board. Now after waiting for some time, we have noticed that the temperature has risen up to 80 degree. At this juncture, I am going to switch off the heating mantle and I am going to note down for every 2 degree fall in temperature, the corresponding value of my microammeter readings. Now the temperature has come to 78. I have to note down what is the corresponding value of my microammeter reading. Likewise, as the temperature falls 2 degree below, that is around say 76, I am going to correspondingly note my microammeter reading. Likewise, I am going to repeat the experiment till the temperature falls to nearly 70 degrees Celsius, that is 10 degree below 80 degree, it has attained the maximum. So for every 2-degree fall in temperature, we are going to note the corresponding value of the microammeter and tabulate in the tabular column as I am going to show in the board. Now, after performing the experiment and noting down the readings of the temperature in the thermometer and the corresponding microammeter variations, we have plotted the readings over here in the tabular column. Now our tabular column tells us the first region, the first column is the current, which is I0 microamperes. The other column is temperature T degree Celsius. So now I have noted for a temperature of 80 degree, I showed it over there. I have written here for you 70 degree. So for 70 degree, the corresponding variation in the current is taken to be around 33, and I have noted it. Now for a fall of 2 degree in the temperature value, say 68, the corresponding value of the current decreases and it is noted as 31. So likewise, for 10 degree fall in temperature, we are going to note down the corresponding changes in the current that is flowing in your semiconductor. So we also note that the current values continuously decreases as the temperature falls down, which tells you that the electrons are incapable of moving to the conduction band as the temperature is falling down. Now to carry on with the remaining part of our calculation, we can see first we have to convert the temperature in terms of Kelvin. What do we usually do? We add to the degree Celsius plus 273 to convert degree Celsius into Kelvin. So I have added 70 plus 273, which gives me 343. Likewise, I am going to change all these degree Celsius value into the corresponding Kelvin value by adding 273. Now the next part of my calculation is I am going to take the inverse of temperature, that is 1 by T, which means I am going to take 1 divided by 343, which comes to around 2.915 into 10 power minus 3, which I have put it as a common in the heading of my tabular column. Likewise, I am going to perform calculations for 341, the next temperature in Kelvin 339, 337, etc. and I arrive at the column 1 by T into 10 power minus 3. And then I have to convert one more, that is the current. I am going to take the log value of the microammeter current I have observed in the microammeter. So log of 33. So that comes to a negative value minus 4 point, you can see this is a point, decimal point, 4.4814. Likewise, I am going to do the calculation for all my current values, and I observe I get a series of negative values in the column log I naught. Right? Now let us discuss what is the formula and where we are going to use these calculations. So to determine the energy gap of a semiconductor, the formula that we are using is E suffix G, which is the energy gap. It is equal to 2.303 into 2 into K into slope divided by 1.6 into 10 power minus 19, converting into electron volt. Therefore, I am going to substitute the value for K, where K stands for Boltzmann constant, and it is equal to 1.38 into 10 power 23 joule per Kelvin. So when you do this bit of calculation, we get the answer Eg is equal to 3.973 into 10 power minus 4, and we are left out with this slope value. So now, in order to determine the slope, we are going to make use of the readings from our tabular column. We are going to plot it in the form of a graph. We are going to measure the slope that is obtained from the graph and substitute in this equation. So let's go about how to tabulate or how to plot a graph. Now, since the log I0 values are negative terms, I am going to plot my graph in the negative coordinate of the graphical axis. So you can observe along the x-axis, I have taken 1 by t into 10 power minus 3 values. So I have plotted 2.915 corresponding to the log I0 value, which is minus 4.4814, which I have taken along my y-axis. You can observe here. So my x-axis denotes 1 by t into 10 power minus 3, and the y-axis denotes log I0. Is that clear? So for the value of 2.915, you relate what is log I0 and you make your first plot. Then repeat likewise for the rest of your readings, and you observe that the points, they are lying in different regions of my graph sheet. Now let me join all these points. I observe that I am going to get a straight line. You can omit some of the points that don't lie along the straight line, which may occur because of experimental errors. Now you take the slope from this graph, name it as A, B and C. So AB by BC. Okay, here it will be BC by AB, that is the reverse of the slope you take and you get a value for the slope, which you can substitute in your formula. So you have already calculated energy gap or the band gap E suffix G, that is equal to 3.973 into 10 power minus 4 and multiplied with the slope that you have calculated from your graph, which you have plotted making use of the readings you have taken from your experiment. So now my answer, you can see it comes to around 0.794 electron volt. So this is the value of the energy gap that has to be provided to this semiconducting material in order to make it conducting. So now we also observe that the value 0.794 is the band gap energy that is specifically for germanium semiconducting material. So we also know that our semiconductor diode we have taken, it is made up of germanium. So this is how we perform the experiment to determine the energy gap of the semiconducting material, which is taken in the form of a PN junction diode. So students, now we have come to the conclusion of this experiment. So I have been teaching you how to determine the energy gap of a semiconducting material taken in the form of a semiconductor or a PN junction diode. and I hope that all of you have understood the demonstration and the experimental techniques that are observed in this experiment, and also you have learnt how to go about with the calculation for the same. So I am very glad to meet you and explain this experiment to you, and I hope to meet you very soon with yet another interesting session of another experiment. So thank you.